Hello, good afternoon, all of you. So we are going to start shortly this second day of our webinar conducted uh, under the by student chapter SPI student chapter in IT Warangal. Welcome all of you in the second day first session of this lecture. Today we are very happy. We are having expert with us, Dr. Nitish Malviya from IIIT Ranchi. He will give in the talk in the topic of the silicon photonics. Hopefully, it will be very useful for all of us because I hope that he will cover all updated topics in this silicon photonics. Now, I will like to request Mr. Abhishek Pathak, who is the president of this student chapter, SPI student chapter in IT Warangal, to introduce about the speaker and proceed the program. Over to Mr. Abhishek Pathak. Abhishek is stating that he is having huge background noise. So, I will read about our invited speaker that is the biodata. So we are very happy to get our expert, Dr. Nitish Malviya. He will deliver the talk on silicon photonics from fundamental to devices. Dr. Nitish Malviya received the PhD degree in electronics engineering from IIT ISM Dhanbad and the MTech degree in optical communication from SGSITS Indore and BE in ECE from RGPV Bhopal, respectively. In 2009, 2012, and 2019, sorry, he received PhD degree in 2019. He received MTech degree in 2012, and he received this BE degree, Bachelor of Engineering, in 2009. So he is very fresh, just completed his PhD degree. He was an exchange research student at City University of London, UK, for 6 months under the Erasmus Mundus program. His current research interests cover a wide range of areas, including silicon photonics, optical modulator, and optical couplers. During the graduations, he was the president of and secretary of OSA student chapter in IIT ISM Dhanbad, and he was also very active member of SPI student chapter. So we are very happy because he knows all this as an active member. He knows all the activities of SPI student chapters. That's why he agreed to give these lectures also. Currently, Dr. Nitish Malviya is a faculty at IIIT Ranchi, Jharkhand. Apart from his academics, he is a faculty in charge of examination, campus management, research cell of advanced communication systems, and hostel warden. So now I would like to request Mr. Dr. Malviya to start his presentations, and we are all eagerly waiting for that.
So thank you, sir, for this nice presentation. So nice this introduction, and also I want to thanks to the organizers to inviting me in this webinar series. So I am a just young researcher now and in an early career. So this is the very difficult to get this opportunity to interact with the participants and get the chances of give the talk and experience in this webinar. So thank you to the organizer to invite me and give me the chance to experience to share my experience with the participants. So now and as well as I want to say to the participants in the during my graduation, the PhD duration, I was a very active member of the OSA student chapter, and that and also I hold the position of a president, and as well as I am a very active member of the SPI student chapter. And during my position hold when I was a president, I was organized so many events like a workshop and the program and like right now the webinar series is very popular. At the time, I'm just organized the different talks of the different speakers, and so I also therefore I was inviting a different professors in our institute. So therefore, I get a chance to interact with the participants of the NIT Warangal and members of the SPI student chapter. So I'm going to accept the invitation. So now I will start my presentation of the on the silicon photonics from fundamental to device. So just I am start my presentation from here. So where is the present now? So I am just click here present now and then share. So I think my slide is visible to all of you. Hello.
Yes, yes, perfect.
Yes, yes, begin.
Okay,
Begin, sir.
can I start?
Yeah, yeah.
Yes, sir.
A presentation on the silicon photonics from the fundamental to device. So it is the more or less starting, the topic is starting from the fundamental to device, but here I'm starting from the device to the fundamental to motivate the students to the motivate, because of the most of the SPI student members are the undergraduate students or the MTech student or graduation undergraduation students. So I am starting, I am just not telling about much more about very high research and the research results. I'm just talking about a device, then I will move towards the fundamentals. How do the device is made? So the first thing, I am faculty at the IIIT Ranchi. Ranchi is the capital of the Jharkhand, and very good environment is there. So this is our institution here. I am working here, and I was done my PhD from the IIT ISM Dhanbad in the 2019. So now I'll start. As the webinar series name is Applied Optics of the Photonics. So first I want to discuss the what is the optics. So here, what is the optics? So when I we was discuss about optics, so a lots of the lenses and the polarizer and detector, we are just use the table and just put all the components together and do the analysis or study of that of the light by using the different material, different components, optical components. So also that optical fiber is having a coupling component. So it is that all about optics. This is I discuss this all thing on the base of my experience. So in the next thing is that what is the optoelectronics. So in the optoelectronics, there's some light is there, we are study about the light, and just the electronics is also involved there. So the laser diode, when we are applying the electricity, then in the output we are getting the laser light, or the lasing action is starting and we are getting the laser light. And in the similar way, the another component is a photodiode. So in the photodiode, when light is falling and it is converting into the electrical domain. So and another thing is that solar cell. Solar cell is very important tool for today because of the energy conservation for the green energy. And the last is that, and it is a LED display. So LED display is one kind of the optoelectronics components. We are just check out the our results on that LED display. We are seeing a lots of LED display in our daily life. And the last one is that a smartphone. And the smartphone is also having the battery that is in output is electronics, and then we are it is converting into the display, and we are seeing the watching the videos, watching the movie, and also we are just capturing the photographs, and that all that thing is optoelectronics devices. So at last, it is a photonics. So photonics is also another branch of the optics. So in that, the photonics, we are just study about a generation of the light or generation of the photons, and then controlling and the other things. So here, this are the chip here. So this is the one single chip there. There is having a different component is there. So I'll discuss in the next slide about much more about photonics, because in this webinar series I am taking I'm just talk about a silicon photonics. So first we'll start with the photonics. What is the photonics? So in the 20th century, the electron is very popular there. So we are generating a lots of electronics devices there. So transistor and diodes, and that by using that diode and transistor, resistor, and the basic components, and they that basic component is making some other components. some active components, and we are just do the different analysis and find out the very good results, and that component is used in our daily life. So that are all about talking about the 20th century. But in the 21st century, photonics is the photon is basic components for getting the different for the application of our daily life. So nowadays, the silicon based CMOS fabrication technology is a very popular. So when we are talking about a previous time, there is having a very huge transistor, then it is miniaturized in the one single chip, and then after what happened, the size of the our chip is miniaturized, and in the one single micrometer chip is having a lots of transistors. So there is having a one mature technology of the CMOS fabrication technology. So the researchers are taking the motivation from the CMOS technology and utilize that silicon-based substrate for the photonic applications, because silicon is a very abundant material and huge, and it is available in the huge amount in the nature. So by using that CMOS silicon-based substrate, it is utilized for the photonics technology, and now become this photonics is a silicon photonics. Okay, so next, we are discuss about what is the silicon photonics. So in the silicon photonics is intricate the best of the photonics and electronics. Okay, nowadays, where lots of application is there of the silicon photonics in the area of the data communication and the telecom industry, because they want a very high data rate, and the electronic domain is sometime is stuck there, and their limitation is come on. So the silicon photonics is give the solution for the high data rate and high data rate applications. So in the one single photonics, and also we are utilize the monolithic chips there. So we are integrate all of the our optoelectronics component in the one single chip, and it has become on the silicon substrate chip, and it become a silicon photonics. So the grating coupler is there, laser detector, optical modulator, tapered coupler, waveguide, ring resonator. So all of these are integrated together, and it is make a silicon photonics. So also, what happened with the silicon photonics? In the previous slide, we have seen that optics and the optoelectronics, that are the branch. Optics is the branch where we are just study about the light and light matter interaction. But here in the optoelectronics, we are discuss about how to the when we are applying the electrons there, what is the photon behavior. But in the silicon photonics, we are just combine the all of the equipments together. Just we are talking about electrical to optical conversion, guidance, controlling of the light, and the detection. Once we are getting the optical light, once and again, and we are guidance there and controlling over there, and we are just utilized for the application, then again it is in converting into the electrical conversion, and that electrical things is communicated to the another device in terms of the data centers. But also we can directly transmitting through the optical fiber from the one place to the another place. So this is all about a silicon photonics. So next thing I want to discuss here, what is the advantage over the electronics. So as we know that the silicon photonics is very popular there, and they are taking the advantage of the CMOS fabrication technology. So in the silicon photonics, there is low operating cost there, because it is consumed a very less amount of the power. Okay, so and the second thing is that low heating components, because of their electron is not moving there, and the photon is the zero mass component, so the low heating component is there. So also there is having a high integration capacity. So in the previous slide, we have seen that all the components is together, like a grating coupler, laser detector, and other optical components is there. So there is having high integration possibility. So there, and also it is utilized the CMOS fabrication technology. So there is having a low manufacturing cost and the high density of interconnects. Okay, so all this provide a very high data rate. So these are all are the advantage and benefit of the silicon photonics over electronics. Also, but the here nowadays it is not a complete all optical chip is there, because there some limitation is there, and researchers is trying to solve that problems. So this is a benefit about silicon photonics over electronics. So how it is possible? Now the CMOS fabrication technology is become a very popular, and it is a very mature technology. And there is having a substrate of the silicon substrate and one layer of the insulating layer, and they are fabricate the different transistor and the basic components, active and basic components of the electronics. So that CMOS fabrication substrate is utilized for fabrication of the optical waveguides and also the waveguide based components like sensors and others. So this microelectronics technology is utilized for fabrication of silicon photonics chips. Why is used? Because there is having a silicon and SiO2. So when we are talking about the optical fiber, there is having a core and cladding. When we are talking about a core and cladding, what happened in the core, the refractive index will be higher. In the cladding, the refractive index will be lower, and low difference. But in the when we are talking about a silicon and SiO2, silicon refractive index is 3.45 around, and silicon dioxide is 1.45 or 48. It is depending on the wavelength. So there is having a very high refractive index contrast, and also by using this mature technology, we are integrate the different components. Also, there is having a low power, which is discussed in the previous slide. And also, the one more thing I have to discuss here, there is having a transistor technology nodes, which is discussed in our next slide also. So by using this CMOS fabrication technology, we can fabricate our silicon photonic devices. Okay. So now our aim is that in the silicon photonics is we have to fabricate or integrate all of our optical component in the one single chip. So this is the one single chip is there. So the integration of the one single chip or in the all of the component is integration in the one chip is called as a monolithic integration. So these are the all component is there, like optical pump, laser, electrical pump, non-linear frequency conversion. There is having a non-linear optical waveguides there, which are used for the optical processing, and the phase shifter and the single photon detector is also there. So that all thing is fabricated on the one single chip. So the one of the one of the very good quote I found in the internet, that is given in this website. The holy grail of the silicon photonics is the monolithic integration of electronics and optics on one chip. So that is that advantage of the electronics domain we are utilizing the photonics domain. Therefore, this photonic industry is going so fast, and the lots of integration is increases day by day. So the what are the impact of the silicon photonics in our daily life? Though, so I will discuss here one by one in the industry in the connectivity from the chip to chip optics. I have also worked on this chip to chip interconnects or chip to chip interconnect technology. So why? Hello, is there any problem? Hello,
Yes, sir. Yes, voice is coming
Yes,
clear.
sir.
everything is going fine.
Yes, sir.
Yeah, fine, fine.
Can I continue?
Yes, sir.
Okay. So the impact of the silicon photonics is in for the connectivity. When we are talking about data centers, there is having a lots of optical, lots of processor is there. We have to just communicate there. So the silicon photonics based devices is communicate that in the data center. Also for the advanced computing, we need to require a very high data rate optical modulators. So in the communication or computing, they are use a very high level of high speed modulators there. On the consumer level, the 3D imaging is also there. Nowadays, the imaging processing is a very popular there. So silicon photonics also impact that industry also. So the lidar is a very you have lots of time you are listen about this lidar. Just like a radar, there is having a lidar there. So that automotive industry and for the army and for the security purpose, the defense purpose, that lidar is very important. And one more example of that, auto driving car is also utilize this technology of lidar. So so the CMOS fabrication technology is a very mature technology for the fabrication. So they are trying to make the different chips on the silicon photonics and apply on this lidar technology, because when the driverless car is there, so they are required they have lots of lidar application there. So that the chip is utilized on that lidar, on that driverless car. So also that now the cloud and datacom is also very popular there. Why? Because nowadays we have just utilized the Google Drive, OneDrive, and other, and also the DigiLocker is also there of the government, and government is also give the cloud there. So how to it is possible, and how to we are do the very fast processing? Silicon photonics is impact on this industry also, and that biomedical application lots of student is working on this spectroscopy and the imaging techniques. So this is also a very important area. Now the COVID is also there in COVID pandemic, and we have also tried to make a device for the detection by using the silicon photonics also, which will be a very, the cost of that technology or that detection technique will be very lower. Maybe in the next future it will be there. So also another application of the robotics or industrial, we have known that in the industrial there is having a lots of things depends on the robotics. So the controlling of that robotics is very important. Means if suppose the company is suppose the industrial area is somewhere else, and we have to just control that all that robotic components. So the silicon photonics and the optical domain is very helpful because of we can control it very fast manner. So these are the different areas where the silicon photonics is impact our life very prominent. So next thing, so this is all about the applications and the basics why we have study about this silicon photonics. But some of the imperfect fit is also there of the silicon. So for the photonic application, the one imperfect thing is there, the electronic bandgap of the silicon make it transparent in the telecommunication range. Our telecommunication range is 15, in the third generation is 1550, but in the telecommunication range is transparent, but there is having indirect bandgap which make a silicon cannot make a laser and other things. So how do we are overcome these imperfections? So the solution is there. We can integrate the material with the indium phosphide and the gallium arsenide and other organic materials to overcome these imperfections. So by using by using the integration of these things, we have removed this imperfection of the silicon and utilized for the photonic applications. Okay, so is that so pure chi2 nonlinearity due to the center symmetrical structures, and also a high chi3 nonlinearity which is limited by the two photon absorption. So how it is solved there? The solution is that we can just combine the electro-optics material and nonlinear material are integrated with the silicon platform to overcome this imperfection. Okay, so through this way we are just remove this imperfection and improve the imperfection, remove the imperfection and utilize for the silicon photonics for the our desired application. So now next thing is that a different other technology is also there, like electronics technology is also mature. Why we are talking about the silicon photonics? Why not we are talking about other platforms like other technologies? So here the one thing is CMOS technology is very mature, and also this material is very available, is very largely available in the nature. So another motivation I am saying, I am discuss here, that this is the first transistor is made by the William Scotley and their fellows, and after some few days this transistor will be the size of this transistor will be reduced. This is the vacuum tube of the transistor there, and now the size of this transistor is reduced here, and then it is miniaturized in the one processor. So the one processor is having millions of the transistor there for the for the electronics processing, and this is the example of that transistor is reducing their size. Similarly, this computer of first digital computer there in the University of the Pennsylvania, INEC. So this is the first computer over there, and nowadays we are using these laptops. So how it is possible? Because of the CMOS fabrication technology, we are integrate a more number of transistors. But now when I have found this picture on the in the Google. So nowadays this, I'm not saying it is the completely bye because this will be give the very good thrill about the basics and the fundamentals, and we are just feel that how to it is how to the things will become like a polarizer and the lenses and the spatial phase modulators and other things. So but now the time is came for the miniaturization. So we have to use that silicon photonics devices to miniaturize all that things on the chip. So So the very become popular lab on chip. So all that components is fabricated on the one single chip and make a one optical chip is there. So now the time has came of this optical chips is there. So how it possible? Because of the CMOS fabrication technology. Now I'm showing here there is having a different technology node in the semiconductor manufacturing. These are the optical waveguides in the range of this nanometer range. So it is starting from that 90 early 90s. About 800 optical waveguide is made around 800 nanometers, and then it is now size of that CMOS resolution of this CMOS technology is decreasing there. And now in the 2014, it is a 10 nanometer. So that fabrication technology is motivated to make our optical devices in this miniaturized level. So nowadays we can make our silicon photonics devices and components in that in the order of 10 nanometers. So in the 2014, there is having a 10 nanometer technology, but nowadays the iPhone and Samsung, they are using the 7 nanometer technology, and the Intel and they are the other competitive companies are working on that 5 nanometer technology. So by using this technology, we can miniaturize our optical component also. So again, the question for the silicon photonics, the another aspect is the economical aspect, because of because nowadays the data uses is very increasing. The voice data uses is slightly, it is getting, it is just matured, that they are not increasing very too much, but the data uses is very increasing. How it possible? Why the data requirement for the internet is increases, but voice is decreasing? Because nowadays lots of video streaming is there, not only for the Netflix and not only for the Amazon Prime, as well as for the education purpose. After that, this COVID pandemic situation, the online meeting is also there, just like that. Here we are just I am talking in the webinar, so that is having a video streaming is there. So that video streaming is getting a lots of data. So this data, how to we are just control this all of the data. So that silicon technology is give the answer. So starting, the silicon photonics is using for the data center is only for the data centers for communicating between the two devices. But nowadays this is the market of the silicon photonics is increasing, and other application is also increases, like for the IoT applications and like for biomedical application and other applications. So this is the motivate to study about the silicon photonics. So also that market forecast is that there is having a billions of chips is making for the data center transceivers, but also the other uses is also there for the fiber optic gyroscope, interconnects, and 5G transistors. So now next, lots of different, I'm talking about a different companies are working in this area. The volume supplier, these are making the silicon photonic devices, and that they are making the prototypes, and the R&D industries are also there. So these are the different working in the silicon photonics. So why they are industries is working so much in the silicon photonics? So in that area, because of in the 2017, when we are talking about a data rate for the our data centers, so it is required the 5 TBps data, terabit per second. But the forecast is saying that it is a 51 terabytes. Maybe it will be a larger, because of the life of the and the world is the life is changing, because nowadays everything is going on in the virtual level. So maybe that rate will be a higher. So this will be a motivate the company to investing their money on the silicon photonics in the future market. Also in the 2006 and 9, there very less company, a very less number of companies is working there. But nowadays, the very big player like IBM, they are working from the last decades. Uh, but there also another player is also investing their money on that silicon photonics. So I am just include this 2 or 3 slides of that market aspects, because of the lots of students is there who are just young mind and maybe an entrepreneur. That is also one of the area you can just start your business and make an entrepreneur. That and also This is the also one area. So now once again I will come to the our presentation of that in silicon photonics. So there is having a different building blocks like a laser, vertical couplers, modulator, and other connector, and then WDM filters. So these are like these components. There is having a different components also making the one silicon photonics. So all that component is having a one thing is a optical waveguides. Okay, so what is the optical waveguides or us photonic waveguides? So I am just introduce here one introduction which are we are studying in the our textbook. So these are the our fundamentals. So these are our fundamentals. This is the rectangular waveguide. Now this the slot waveguide and the silicon nanowires. So these are the different type of the photonic waveguides. Okay, so these waveguides is a very building block of the this by using this waveguide we can control the light as well as we are applying the electric field there, and by using the electro optics effect we are modulate the light. By using the nonlinear optics we are just control the phase of the light by using this waveguides. So here I'm just also introduce that how to that fundamentals is become a technology or come to the into the devices. So when we are talking about a simple rectangular waveguide, what happened here? And also move towards the one revolutionary waveguide is there. So this is the rectangular waveguide there, and there's silicon substrate, SiO2, silicon, and then cover. So when the size of the device is comparable to the our operating wavelength, then it is 50 nanometer. Is here I'm showing you. But when what happened when we are just reduce the size, because now I'm talking about a miniaturization of the optical devices in the photonics. So when we are miniaturizing this, reduce the size of this optical waveguide, then what happened? The discontinuity in this boundaries optical field is very high. So here most of the electric field is confined in the core region, but the sum of the light is in when we are the waveguide is it is approximate between the 1550 nanometer and 500 nanometer. So there is having discontinuity is there. When we are reducing the waveguide into 200 nanometers, then what happened? A more number of light is confined in this discontinuity in the boundary, and then most of the confinement of the light is reduced. So this is the disadvantage. But now once again, if in case we are adding the another waveguide together, then what happens? It make a silicon waveguide. So it is a 200 nanometer. We are putting the another 200 nanometer waveguide. This is a silicon wave slot waveguide. So the slot is there. So the light is just leak out from this boundary. It is confined in this narrow, low index narrow region. When we are talking about optical fiber, what happens? The light is confined in the high index, but here the light is confined in this low index region. We have we have already discussed in the textbook about directional couplers, but the size of that waveguide is very high, and this the distance between two waveguide is very high in the range in order of the micrometer. But all things are in the 200 nanometer. It is a 200 nanometer. Height is 220 nanometer. Why it is 220 nanometer? Because most of the CMOS technology is making a 220 nanometer technology. It is a very popular technology. So here we are made the silicon slot waveguide. How it is made? How to we will do the analysis? These are the fundamentals. So once again, we are seeing here. This is the 200 nanometer waveguide, and the channel distribution is there. So we are starting the study with the 1550 nanometer, and we are reducing the width of the our waveguide. So here the distance between the two waveguide is approximate 50 nanometer, and we are just reducing the size of this waveguide. The in the previous slide we have when the size is reduces, then this discontinuity is occur. So here we are just increasing, just reduce the optical waveguide size. So what happened here? Most of the light is leak out, which is confined in this narrow slot region. So this is the all about how do we are just confined the light here. So these are the fundamentals, and just we are utilize that we are put the another waveguide, and the discontinuity of the electric field is made together here, and this slot waveguide is confined the optical waveguide. The light is leak out here. That leak out light is confined here, and we can utilize these devices for the different optical components like a modulators and and other things. So how it will possible? Now again, we are talking about a boundary condition, the fundamental things, the continuity of the normal component of electric flux density at the refractive index boundary is continuous. So D slot is equal to D slab. So this is the slab and this slot is equal to here. So now also the normal component of the electric flux is discontinuous here, but the tangential component is continuous here. So by using this boundary condition, we are analyze this waveguide and we have find out the answers of that question, how why it is confined the light in this narrow low index narrow region. And so this D is equal to this equation, and we have find out the electric field in the slot here, which is equal to n square slab upon slot n square slot low index quantity will be more than one, and we are getting the high electric field in this narrow region. Also that in the conventional waveguide there is having dimension is multiples of the wave lambda, so the light is confined in the core region, but the light can be trapped in the low index region when the dimension is less than the wavelength, means it is very less than the wavelength. Okay, so these are the fundamentals is already given in the our textbook. We are studied in our classroom study when we are study about optics, integrated optics. So these basic fundamentals give the answer of this question, why the electric field is confined in this region. Okay, so next I'm just discuss the how to we are utilize that fundamental for analysis the results, and it will become a technology. So here this is the waveguide here, and this is the effective index method. So here it is a complex problem there. We have just two different waveguide there and SiO2 and silicon substrate there. So we know that the slab waveguide analysis of the slab waveguide in the our textbook. So we are just divide our waveguide into the two part, horizontal waveguide and the vertical waveguide, and make it together, and the result we are combined together. And then what happened it, so when we are just analyze it that horizontal slot waveguide and vertical slot waveguide, then what happened, the output will be given to the horizontal waveguide, put into the vertical section, and it is give the output which is a solution of the overall waveguide. So this is happen with the effective index method. So by using the effective index method, we are just calculating the what is the ex for this xa region, and then for this region this is the electric field and this one is electric. So this is the electric field distribution of the slot optical waveguide. So this is, by using this equation, I have draw this graph of the distribution of the slot optical waveguide. So it is also compared with the simulation software, because as for checking the what we have done is correct or not, we are just we check with the simulation software. Similarly, that another thing is that we have calculated the magnetic field, and once again I have just compared our results with the with the simulation software, and very agreement with that. So in this manner, by using this equation, we have understand and we have find out the answers why the silicon slot waveguide, and also for finding out the effective tangential equation, and solve this equation by using the bisection method, and we are getting the solution of the propagation constant. We can find out the propagation constant. So this is the way we are use the fundamental for analyze the which is become a technology now. So these are the once again we are use this confinement factor formula and effective index formula, and waveguide and effective mode area for the slot optical waveguide, and utilize that effective mode area for the non-vector is utilized for the electro optics modulator. So I have wrote here, so a lots of different equations we have studied. So here given by Einstein, everything should be made as simple as possible, not simpler. Means you have to reduce to divide your complex problem into the smaller one, and until as it is not a simpler. So what when we are divide our problem, there is we suffering things we have also limitations there, but try to make that. The next thing is that slot waveguide modulator. The components silicon photonic chip later. So here I am discuss the slot waveguide based modulator. So when we are talking about a slot waveguide based modulator, there is having a problem. We have to confine, we have to just optimize that structures. What is where we have put this? We have just optimize this one. So I'm just solve the problem, and we have just optimize the silicon photonic chips. So on the basis of this confinement factor, when we are increasing the silicon waveguide width, we have find out the confinement factor higher at the certain point. We have choose that point. Similar manner, we are changing the slot waveguide, and we have find out some confinement factor when it is the point where we have find that we are optimize our slot waveguide structure. And then once we have optimized our structure, and when then I will utilize this structure for the similarly that these are the basic fundamental equations like effective index. In the effective index we have find that one real part there, and in this imaginary part we can find out the absorption loss of that at slot optical waveguide. So if in case we know that slot absorption loss is there, either it metal waveguide is there. So the metal waveguide is having a very high effective index. Oh, sorry, high imaginary index. So when we are putting with the our study or we find out the some imaginary part of the effective index. So the basis of the absorption, we can optimize our electrode distances also. So here when we are increasing the distance, as usual the absorption loss is decreasing, so we can find our trade-off point where we can put electrodes in an optical modulator. So in the similar manner we are just applying the electric field there. When we are applying the electric field there is having just previously we have discussed that electric field is optical electric field is confining the slot optical waveguide. Similar that the voltage is there, so the electrical field is so that will be used for the calculation of the phase modulation. So we know that this is standard equation. So this standard equation can be give the variation of the refractive index due to this applied voltage. When we are applying the voltage, there refractive index is changing. Due to this refractive index changing, the effective index is changing, and by this way we are find out this phase changes. This phase change is can be used for calculating the modulation purpose. So these are the fundamental equations which are involved in the our silicon photonics devices. So this is the flow chart. As I have said that make the your complex problem to similar, smaller, simpler. So we have made a one flow chart for doing the my research on the silicon modulator. So you can also make the your flow chart for your study, and sometime you have find out any problem, then you can change it and improve it. Another problem is the data rates. So we need a very high data rate, means we need a very small width of the optical pulses. So by using the non-linear silicon slot waveguide, we can generate the ultra short pulses on the on chip. So for that purpose, we are utilize the silicon organic material there. So nowadays we can use a fiber-based system for generating the ultra short pulses that is required a very high power, and they have a lack of compactness, and they have introduced some pedestrians. So but when we require the on-chip pulse compression, it is required a low power, say a short interaction length, and low attenuation with the high confinement. So this is the advantage of a silicon photonics. So we need this one. So for that purpose, we are add a organic material with the silicon slot waveguide, and it is make a silicon slot organic waveguide. So when we are just combine the organic material with this silicon slot waveguide, means in the low index region we are fill the our organic material. and we are converting this slot waveguide in the non-linear waveguide, and we are utilize that non-linear phenomena for our application. So for that purpose, I have done just pulse compression. There is having proof velocity dispersion and self phase dispersion in a non-linearity. We are just control together and cancel out there. In that case, we are just apply the initial chirp on the pulses, initial pulses. So by using this initial chirps, we can control our. Discuss about this thing because now I want to motivate the student. These smaller things which are studied in the classroom, which will be utilized for the future technology. So here, another type of the slot waveguide is a horizontal slot waveguide is there. So in the slot waveguide, there is having a slot is presently there. This is the made by the silicon. This is another made by the silicon. In between that organic material is PTS. So PTS is there having some advantage there. So this is the nonlinear material. It is provide a very high nonlinearity, and this slot waveguide is confine the most of the light in this slot region. So by using this we can very high non-linearity in the very low electric in very when we are applying the very low electric field, and then we are getting the very high non-linearity in this slot is horizontal waveguide. So there is having also I have similarly, there is having oh sorry, this is the electro-optics material is there, and also I have have a one slide of this nonlinear material, but not here. So this is the electro-optics material. So next, I am discuss the result of this horizontal slot waveguide. This is the horizontal slot waveguide, and this is the electric field distribution of the our horizontal slot waveguide, and this is the peak compress over there. So when we are when we are utilize the our Schrodinger equation and find out when it is moving from the zero distance to the another. So these are the Schrodinger equations there, and which includes the higher order equation and Raman scattering, and then it is reduced with the nonlinear Schrodinger equations. And these are the equations are also given in the textbook, and this is utilized for obtaining the pulse compressions. And also there is having a lots of nonlinear applications. So this is the one basic thing: electric effective mode area, nonlinear coefficient, and the GBD coefficient is there. So this is the one diagram there. So this is the unchirped pulses is there, and then it is a chirped pulses and chirped negative GBD there. So when it is combining together, we are find out the very good pulse compression factor here. When we are increasing the our initial chip in the negative initial chip there, so we get a pulse compression. So this is all about I want to discuss here motivation behind the study of the silicon photonics, and as well as this is all about the silicon photonics. And now this time I have completed I think on time, so 5 minutes is time for the questions. So now
Sir, one question is there in chat box.
1 minute, I want
Please,
to change this slide to change no.
I,
Yes.
Mr. Gamal Jaz, he said that a very teeny optimization detail as simple as possible.
Yes, that's me. That's my question. Hello.
Hello.
Yes.
Is there is a one question, sir? A very teeny
Yes.
optimization detail, as simple as possible, not simpler. A little bit illustration, please.
Hello. Yes. My voice is audible.
Now audible, sir.
Yes. 1 minute. I want to switch my screen to the chat box. Okay, where it is? Yes. chat box. So very teeny optimization is giving here as simple as possible, not simpler. A little bit in illustration, please. Okay. So actually, when I was a student during my PhD, and I am getting different lectures there. A lots of lecture I am getting there, having a lots of research problems, which is also already we are studying in the different research papers. So now in this talk, I am trying to that which is the fundamental things you are studying in the classroom, which is very important and which will be utilized for the your research also and that device also. So I'm just illustrate one more thing. So like that, in the previous, I have solved the problem of this optimization. So first of all, I have to just optimize this structure. So I'm for that purpose, I'm divide my problem. First of all, I have just increasing the waveguide width, fix our slot waveguide width here, and increasing the our waveguide width, and find the our confinement factor. So this is the one way, make it simple it, and we have find out the higher confinement factor here. In the similar manner, in the second step, I have just fixed our waveguide width and increasing the slot width. So in that case, we have find the confinement factor here. So the first phase of the optimization is complete here. In the second step, we have to just optimize the what is the distance of the electrode. So the how to utilize, how do we are optimizing. So when the electrode is putting very nearer to the silicon waveguide, so metal is very lossy, so their absorption coefficient is very large. So what happened? Most of the mode is disappear here, and that will be absorbed by this metal layer. So for that purpose, I am just increasing the electrode distance here and utilize these equations and find out the absorption coefficient by through this negative effect, imaginary effective index, and find out this absorption coefficient is there. And through this way, I have just optimized our electrode distance here, which is equal to 1. Okay. So I think you have get the answer of your question.
Yes, but my question is, in our optimization problems, actually we are getting step by step enhancing
Yes.
our results until we reach the optimum value. So that if we
Yes,
are
yes.
setting our goal to get the simplest
Yes.
case, we shall not reach it yet. So that we are going step by step. We cannot reach our goal in a single step. You got my point, Doctor?
Yeah. We cannot reach. So we have just divided steps. First of all, we have to just optimize our waveguide weight. Then the height is fixed here, but because of due to the limitation of the silicon chip, there is having 220 nanometer. So first we have just changed the waveguide width, and then change the slot. In the you have to just divide your optimization process for the different parameter, and you will just make it simpler that for the optimization. So my motivation behind that asking this thing is that just you have to divide that whole area and make it simpler.
Okay,
Means you
Doctor,
have to
thank you.
understand, you have to learn, and this you have studied in the textbook that basic equations will be give the your answers.
Thank
Okay,
you, Doctor.
second thing is that I have different questions. PDF of the material equations were useful. Okay, so you can I have give the, if you can drop an email, I will give you the what is the source of that material. So I will give you. Okay. Hello. Hello.
There is some more questions.
Can we use the silicon photonics for the making qubit? Oh yes, you can, but I have very little knowledge about this qubit